In this video, we're going to look at computing a surface integral over a surface that I'm going to label sigma. And it's the portion of the cylinder given by x squared plus y squared is equal to 4 between the heights of z equal to 0 and z equal to 1. And the function that we're going to integrate over that surface will be z squared. So here we have the surface integral over sigma of the function z squared. And the ds here is conveying the fact that we're working with the surface integral. The terms of my integral are in some sense weighted by the surface area of the surface, and that's what the ds is representing. I've drawn a picture of the cylinder. Here is x squared plus y squared equal to 4. It's vertical, parallel to the z-axis. Because it's x squared plus y squared is 4, 2 squared, we're saying that the radial amount, r squared, is equal to 4, so r is radius 2. The radius out here is 2 units. One way to calculate a surface integral is to parameterize the surface. And any way that you can manage to do that, there's no single parameterization for it, but any convenient parameterization will do. And what I see when I look at the picture, I kind of see a vertical parameter, and I see a radial or angular parameter going around the circles there. So that suggests to me I should do something that's somewhat trigonometric. I'm going to have two parameters. I'm going to call them u and v. And I'm going to take the u to determine sort of the angular part of my surface. So I'm going to have 2 times cosine I plus 2 times sine of u times j. And I'm not quite done yet, but if I was just to vary u, what I would expect to trace out is a circle of radius 2 in the xy plane. And then I'm going to let v indicate the z component, the vertical direction. And so I'm going to use that, and I'm going to add to that v times k. And as I vary v only but keep u fixed, I'll move up one of these lines here for a given choice of angle u. It's not enough to just give a parameterization's formula. You also have to give the domain of the parameterization. Again, u is representing sort of this angular part, and we'll need that to go from 0 to 2 pi. And then v is indicating the vertical component, so I'll need that to go from 0 to 1 because that's what I've specified. The z coordinate on my surface is trapped in between 0 and 1. The next thing you'll need in order to apply the change of variables theorem we talked about is the length of the cross product of the partial derivatives of your parameterization. So you're going to take r sub u. That means to differentiate with respect to u, so I'll have minus 2 sine of u for the I component. Take the derivative here with respect to u will be 2 times cosine of u for the j component. And finally, the k component has no u's in it, so that's done. There's no other term. That will be 0. For v, kind of the analogous thing here, this has no v's in it, this has no v's in it, and this term will be 1 when I differentiate, so the derivative with respect to v will be k. And in fact, I've plotted these vectors at this point right here. You can see the computer's plotted some vectors for us. As I change u and keep v fixed, I should go around one of these circles, so ru will be tangent to a circle, and that vector there is in fact ru. And then v, as I vary v, I should move up the cylinder and not change my angular component, so I should move right up the red arrow there, and in fact that is rv, tangent to the cylinder and pointing in the vertical direction. Their cross product, if I take Ru cross Rv, will be normal to the surface, and in this case, because of the order that I just said, it will go into the cylinder according to the right-hand rule. So that will be Ru cross Rv. You can compute that cross product. It's a vector. I get it by doing a determinant expansion. So I take my components for Ru, I take my components for Rv, and then I expand that out. For the I component, it's going to be 2 times cosine times 1 minus 0 when I go this way. For the j component, I'm going to have minus 2 sine u times 1, but because the j component has this traditional change of sign, it'll become plus there. And then finally for the k component, there's zeros in this row right here, and so I'll get no k component. And then you can see that in the picture, the cross product's pointing parallel to the xy axis. It's not pointing up or down. Finally, you need the length of that. So take their components and square them, add them together and take the square root. This will be 4 times the sum of the squares of the cosine and sine, and of course that will simplify to 2 using the familiar trig identity. Now we're integrating a certain function, in this case it's z squared, over that surface, so you need to find the value of your function in terms of your parameters u and v. So I need to evaluate f over the surface. I'm going to take f at 2 cosine, 2 sine, and v for x, y, and z respectively. I'm getting them from my parameterization. In this case, I only care about the z coordinate, and I'm supposed to take v and square it, so it would be v squared. And in fact, look, v is our z coordinate in our parameterization for this surface. And we're ready now to do the integral, and we do that with change of variables. The surface integral we're calculating can be calculated in terms of our parameters by integrating our function v squared. We must also apply a factor of the length of the cross product, that is the cost of converting to the parameter integral. So in this case it's 2, and I'll get a factor of 2, and then we integrate that with respect to our parameters in either order that's convenient for you, dv and du. We'll set that up as a double integral. U varies between 0 and 2 pi, and then v varies between 0 and 1, and those are our limits of integration. Not hard to, I'll let you do the details, but not hard to do the integral here. I'll have 2v squared, I'll integrate that, I'll have v cubed over 3, and I evaluate that between 0 and 1. You'll get 4/3, and then you evaluate the other integral with respect to u, you'll get a factor of 2 pi, and we'll get 4 pi thirds as a result.